In the last video, we looked at different methods of visualizing our data when we are working with categorical data. In this video, we are going to be looking at ways to visualize quantitative data. The first thing that we're going to start with is frequency. All right, so we're going to kind of go through quite a few things before I start putting examples on the board. Hopefully that'll make sense at the end of it, and we'll be able to do it all at once. Now, when we are working with quantitative data and we are trying to create a frequency or relative frequency distribution, it's a little bit different than when we're working with categorical data. Categorical data already has pre-existing classes and categories that we can work with, right? That's pretty much all nominal data is. It's just categorizing these groups, and then they're pretty singular, right? If we're doing something like favorite color, right? Red is red, that's its own group, right? However, when we're dealing with quantitative data, especially if we're dealing with continuous data, then, right, there's an infinite number of kind of categories or classes if we use each individual one, right? Even if we're not doing that, there's still more categories than we would want if we did each individual number its own category. So instead of doing that, what we're going to do is formulate our own classes, right? I am just going to kind of talk about this in overview. If you want more information about how to do this, you can look in the book. However, in my opinion, you're never going to do this by hand. So I'm not going to go through the process of doing it by hand. Also, it's really pretty much just guidelines for creating these things, and they're not hard rules. So you can kind of discover those on your own if you are interested. But most of the time, if you are going to be creating something like this, you're going to do it in a statistical software package, right? You're not going to be creating these on your own really ever, all right? But that being said, kind of just reiterate, we don't have those pre-existing classes with quantitative data, right? So we would have to create our own. Kind of some steps and guidelines for how to do that are in the book, right? But once we have created those categories, right, then we would place our quantitative data into those different categories, right? So the classes or the categories, they would be number ranges, right? So in the example I'm going to give in a second, right, the first number range is 0 to 19. Right? So any numbers falling into that 0 to 19 range would be put into that class, right? And so that's how we would find our frequency, right? So our frequency would just be found by saying how many of the numbers in our data set fall into this class, right? It's a little bit, there's some small differences there, but again, if you're interested in those, you can check the book or look at it online. I'm more interested in you being able to read one of these than to make it yourself, right? But that is what that means, right? So that's how we would get the frequency, and then the relative frequency would be done more or less the exact same as we did it for the, not more or less, it's done exactly the same as we do for the categorical data. We would take our frequency divided by the total number of observations. All right, so where we get more of a difference is we have a couple of extra things for quantitative data that we can use, right, that we can do versus our categorical data. All right, one of those is what's known as the cumulative frequency. So, cumulative frequency, all right? This is the sum of the frequency of a class and all preceding classes, right? So, hopefully to help us kind of understand what this means, right? Cumulative right? If we have a cumulative final, which we do in this class, it means that it's going to contain material from the entire class, right? And so that cumulative is why we are adding all of the frequency for all preceding classes into our thing. So as we go from the smallest number to the largest, right, or the smallest class to the larger classes, right, that cumulative frequency is going to get bigger and bigger, showing us kind of up to this class, right, how many observations are in this class or below it, right? That is what that cumulative frequency is going to be showing us, right? And we'll look at more of an example in just a minute. But before we do that, let's also just get the definition up for, again, another related topic, which is cumulative relative frequency. All right, you can probably work out what this is just by the title, but I'll go ahead and write down the definition anyways. All right, so the cumulative relative frequency is the sum of the relative frequencies of a class and all preceding classes. So again, it's exactly the same as the cumulative frequency, just for the relative frequency. All right, so now let's look at some of this stuff in action. We'll see if I can actually fit this entire chart on this whiteboard, but hopefully I can. It'll be really boring for you guys to watch me fight this for 10 minutes trying to get it to fit, but we'll see. All right, so we would have our classes, right? And our class is going to, again, we would have manufactured these if we're doing them by hand, but we're gonna kind of gloss over that. All right, so our classes might look something like this. This is in 20 unit increments of 20, all right, except for this last one, which is, I think, technically 21. But those would be our classes. Again, when we are looking at our frequency, any numbers that, there's a little bit more to it than this, but any numbers that fall between 0 and 19, all right, those would fall into that class, and our frequency would just be the number of observations that fall into that class, right? I haven't given y'all any information on this either, so yeah, I'm just writing this stuff down. This isn't coming from anywhere, so if you're not sure where this stuff is coming from, don't worry, I'm just making it up. The numbers, not the like definitions and stuff. All right, to save space, I'm going to do some heavy abbreviating. So frequency, relative frequency, RF. So again, frequency, we would have to have our data. We would kind of go through the process, right? We're just going to take this as a given, right? Then when we went to find our relative frequency, we would just divide the, so the total is 16. So yeah, you can add those up, see that it's 16. We just divide each number by 16 to get our relative frequency. So we're going to get right, we would get our relative frequency, right? Those should add up to 1, although if I left it the way I normally did, this would be a case where we'd have a 1.001, but regardless, that would be fine, right? Just do the rounding, right? But that should be our relative frequency. 3 divided by 16 would be 0.1875, round to 0.185, although technically we should round to 0.187, right? Anyways, right, so that would give us our frequency and our relative frequency for that quantitative data. Then we could move on to our cumulative frequency. All right, our cumulative frequency, again, when we go to do the first class, all right, the cumulative frequency for the first class, which is the 0 to 19, then we're gonna take the frequency of that class, which is 3, and add to it all preceding classes, right? This is the first class, there are no preceding classes, so the cumulative frequency for that first one would be 3, right? Then we would move on, so 8 plus the frequency of all previous classes, so 8 plus 3 giving us 11, then 12, then 14, and then 16. All right, so just like how the frequency should add up, right? The sum of this column should be the total number of observations, and the relative frequency should sum to 1. The last value in our cumulative frequency should equal the total, all right? Because again, we're essentially building up to the total number, right? So that last one, the cumulative frequency for our last class should always be the total number of observations. All right, then we would have our cumulative relative frequency. So again, a very similar thing with this first one. There are no preceding classes, so 0.188. Then for the next class, we would say, right, the relative frequency of the class we're looking at, plus the relative frequency of all preceding classes, so 0.500 plus 0.188 to give us 0.688, so on and so forth. Similarly with all of these other ones, there is kind of a thing that we can look for with this cumulative relative frequency, and that is the cumulative relative frequency should equal 1. All right, so if our cumulative relative frequency doesn't equal 1 for the very last category, not the sum, but for the very last class, if it's not equal to 1, all right, we might have made a mistake. All right, so just like with that information, just like when we had our frequency and relative frequency distributions and used those to create our bar charts and pie charts for categorical data, we can do something somewhat similar to that with this quantitative data. All right. Now, normally you're gonna do this in a computer program. You're not even gonna, most of the time for this next thing we're gonna talk about, you're not even gonna make this distribution chart that we just did. You're just gonna have the program generate this for you. But this is a histogram, right? Or what we're about to talk about is a histogram. And really what a histogram is, when you really break it down, is it's just a bar chart for quantitative data. All right, that's basically all that it is. There is an example of a histogram in that PDF that got posted along with these videos. And you'll see that it is slightly different from other bar charts, right? Those categorical bar charts. When we're looking at those bar charts that are based off of categorical data, there are gaps between the bars. whereas we don't have those for histograms, right? And that's because, especially when we're dealing with continuous data, right, there's no real cutoff, right? It's kind of a fluid thing. We're moving through any of those infinite number of possibilities. So our bars are going to butt up against each other. All right, that doesn't mean that there can't be spaces. If there's no data in a specific class that was created, right, then there's going to be a gap, but only because there were no observations in there. All right, but other than that, they are just a bunch of bars kind of smashed against each other. All right. What we use these histograms for is to look at the distribution of our data, so kind of see where is most of our data at, and is there a lot that's really different from the stuff in the middle. We're going to talk more about distributions. I don't want to get too big into it right now, but that's what those histograms are for. Right? They show us the shape of our data is essentially the same as saying the distribution, right? And gives us some general ideas about a lot of terms that we haven't covered yet, right? Kind of gives you an idea of the mean or the median, gives you an idea of what we call variance, so on and so forth. We're going to cover those in the next chapter. All right, but that's what histograms are. All right, they are very useful. These are probably one of the things that if you continue in statistics, you'll probably see these most out of just about anything else we're going to cover in this video, with the exception of maybe one thing, right? But these are very useful, right? They're going to pop up pretty regularly. All right, the next thing we're going to look at is, actually, I'm going to move some stuff around. All right, the next thing is dot plots. All right, dot plots are very similar to histograms, but in one, there's one key difference. One of the benefits of a dot plot is that with a histogram, right, the height of the bar just shows you kind of the frequency for that range of numbers, but it doesn't tell you which exact numbers, right? So if, for instance, we were looking at our frequency distribution from earlier, and we looked at that 0 to 19 range, right? And we see that there are 3 numbers, right? We got a frequency of 3. That means there are 3 numbers in the range 0 to 19, but we don't know which numbers, right? It could be 3 zeros, it could be an 8, a 12, and a 14. We don't know. All right, so we lose that information about individual data pieces, points, but we don't do that with dot plots. All right, there is an example of a dot plot underneath the histogram in that PDF, and it's done using the same data, so it's going to look almost identical. The only difference is that for the histogram, there are going to be bars that are smashed up against each other. For the dot plot, it's just kind of dots in a line. All right. They're going to look very similar. They're going to give you a lot of the same information, kind of give you the idea about the distribution or the shape of the data. Dot plots, however, are probably less commonly used than the histogram, partially because once you have a large data set, so if you have a lot of data, a lot of observations, then being able to pull out those individual data points doesn't matter as much. And also, once you put it into a reasonably sized chart, you can't see them anywhere. Anyway, all right, they'll just kind of bleed together, and you won't really be able to get the kind of information you're looking for from a dot plot, especially if the range of the data is really large, right? If you go from 0 to 1,000,000, it's going to be hard to get those individual data points, right? And so you'd more likely want to go and use a histogram. All right, but again, they are used somewhat, just not as commonly as those histograms. Right, along the same lines conceptually as the dot plot is the stem and leaf display. I'll go ahead and tell you, I have never seen one of these actually used other than in a textbook. That doesn't mean that they aren't used somewhere, but I haven't seen it. However, it is in the book, so although that doesn't always stop me from just cutting stuff. It is in the book, so I'm going to show it to you. All right. Again, though, it's arguable how useful this is. All right, so what a stem and leaf display is, it's a way of, just like with the dot plot, of maintaining those individual data values while also trying to condense the data into something that's a little bit more, well, one, condensed, and then also visually kind of appealing / allow us to visualize our data a little bit. All right, so I'm gonna show you the steps of creating a stem and leaf display, and then I'm gonna make a very small one. All right, the first step when making a stem and leaf display is we need to sort our data, all right, get it in ascending order, so from smallest to largest. The next step is to find the minimum and maximum value. So if it's in order, you basically already done that. It's the beginning value and the second and the last value. All right, this is to determine what your stems need to look like. All right, the third step is to set up our stems. And the fourth step is to fill in the leaves, all right? So, depending on how much you remember about grade school math class, this might all make a ton of sense to you. If not, that's okay. We will walk through this real quick. All right, so I'm gonna just put a couple of numbers up here. All right, so here is our data set, all right? 86, 79, 43, 58, 43, and 50. All right, so the first step we're going to do is we are going to put our data in order. So once it is in order, then we will look and find our min and max. Our minimum is 43, our maximum is 86. All right, and so kind of this step and the third step go hand in hand, and that is kind of setting up our stems and knowing how we need to do that. So this is the starting point for our stem and leaf display. All right, so the stems are going to be kind of in this case it would be the tens place. All right, so we're going to be chopping these values down. So the stems are going to be the tens place. So we're going to look and we're going to say, well, we got 40s through 80s. All right, and so we want those all represented in our stem and leaf display on this stem side. All right, so we know we've got 40s through 80s, so we need a stem that is 4, 5, 6, 7, and 8. All right, so again, so this stem of 40 is, or stem with a stem of 4, that's 40, 5 is 50, 6 is 60, so on and so forth. All right, once we have those stems there, all right, we can fill in the leaves. All right, so what the leaves are is just the ones place in this case. All right, so we're just going to put down, all right, that ones place for each value. All right, so starting at the lowest number, 43. All right, so it's in the 40 stem. All right, and then we're gonna have 3. All right, so that is that one taken care of. All right, we have another 43, so we're gonna put another 3 in the leaf in the 40s place. All right, and then we're gonna move on, do it for 50. All right, so that's a 0, 58, that is an 8. Right, we get to the 60, we don't have anything, so we're gonna leave that blank. All right, we're gonna leave those leaves blank, move on to the 70, 79, 80, we have that 6. All right, so what this allows us to do is, if we had more data than this, it would be a little bit more apparent, but it does give us an idea of the distribution, because if we have a bunch of stuff in the 40s, this leaf line is gonna go keep going out. All right, we're gonna see, oh, well, there's a lot of data in the 40s, right? So on and so forth, right? We can pick out these individual data pieces, and we can use this, right? If we were presented with this stem and leaf display and asked to do some math with it, we should be able to, right? Because we can just look at it and say, well, what numbers are there, right? Well, 40, and here's a 3, so that's a 43. There's another 43, a 50, an 80, nothing in the 60s, right? 79, right? So, or 7 and 9, so 79, 8 and 6, so 86, right? But that is a stem and leaf display. All right, again, don't see them very commonly, all right? I haven't seen them out in the wild very much, mostly in math books. But again, that is one way that we, or another way that we can display our data, get an idea of that distribution of kind of that shape of our data while maintaining those individual data points. Right? However, because we are trying to maintain those individual data points, it has some of the same disadvantages of a dot plot. Namely, if you have a ton of data, it kind of becomes less useful because the display is just too big to really be of any use. All right. All right, and then the last type of display we're going to talk about is a scatter plot. All right, so a scatter plot one, I'll tell you that this isn't actually in chapter 3, I think it's actually in chapter 4, but this is the section on visualizing data, and I think this is a better place for it. All right, so a scatter plot is a graphical method used to display the relationship between two variables. All right, so this is when we're looking at two different variables. So really classically, I'm sure you'll all kind of relate to this. It's that XY plot. That's what a scatter plot is. We have two variables, X and Y, right? And we're seeing how they relate to each other, right? That's what a scatter plot is showing us. All right, it doesn't really matter what X and Y are. well, I guess it kind of does. It depends on what you're looking at, but we're just gonna make some up. All right, so let's say this is what we've got. So let's say that our one variable on the y-axis is the number of dogs you have owned over your lifetime, and let's say the x-axis is the average number of miles you walk per week. All right, so again, these don't really matter, but just a silly little example, right? All right, a very simple scatter plot might look like this, right? We know how X and Y plots work, all right? So let's say this data point right here that I'm about to circle in red, right? This is telling us that, you know, for this individual, right, they owned Y amount of dogs and have an average of X miles walked per week. All right, so that's not really the main point of this, all right? But what the scatter plot lets us do is look at that relationship. Look at the relationship between one variable and another. So we're not going to get too heavy into this. I'm just going to say this stuff. You don't necessarily need to. Go ahead and write it down, but I'm not going to write it down. All right, it can give us the idea of the relationship. Right, so if our data moves in this direction, right? So from the origin out and up, right? That's going to indicate a positive relationship, right? One in which as one variable increases, so does the other, right? If it was in the other direction, right? So let's say we started up here in the top and moved down this way, that would indicate a negative or inverse relationship where as one variable increases, the other one decreases and vice versa. All right, we're not gonna use this too much. You're gonna see it more if/when you go on to stats 2. All right, this idea of kind of these types of relationships, right, are gonna be a lot more important. All right, but that is all for chapter 3. So we will go ahead and end there. The next chapter and the next set of videos are going to be focused on common statistical methods. So we're going to start actually doing math at this point, which is very exciting. I'm sure you're all very excited about that. But we're going to go ahead and start doing math. We're going to look at things like the mean. We're going to look at variance. We're going to look at what are called quartiles and percentiles. But that's what we have coming up in the next couple of videos. I will see you then.